Welcome to today's episode of BCME, BC Made Easy. My name is Johannes Joe.
My name is James Fan. I'm Andrew Go.
The topic we'll be covering today is limits. Calculus is all about the scary words. There's differentiation, integration, convergence, you name it. But before all those scary words, there's one little word that you'll need to know first, and that's limits. Limits is a very fundamental concept in calculus. It is necessary to grasp this concept in order to learn more advanced topics in the future. Limits is a different way of thinking about numbers and variables, which allows us to evaluate multiple functions, as well as define derivatives, a topic that we will talk about in the future. Alright, let's go over the basics. Here is the standard notation of limits. Most of the limit problems you'll encounter in the future will be written with this notation. As you can see, in this standard notation, you first write LIM and then write x arrow some value underneath. On the right, you will find some function of x. Basically, this notation indicates that in that function of x is gradually getting closer and closer to some value a within the function. Here is one of the most basic examples of a limit. As you can see, in this equation, x is gradually approaching 0. Now, if x is gradually approaching 0 within the function x plus 1, we know that the function will gradually approach 1. And therefore, to evaluate this limit, we can say that the function will equal 1 when x approaches 0. This is pretty much the simplest explanation of limits that we can give. Unfortunately, not all limits are as friendly as the one I showed you. For example, what would happen if x was on the denominator and x approached 0? Let's go into a more detailed explanation of limits.
Hi, I'm here to define limits and to teach you how to solve them. There are multiple definitions for limits. The mathematical definition of limits is known as the delta epsilon equation, and I will be explaining it. Limits is with the delta epsilon equation. The delta epsilon equation uses variables delta and epsilon to help calculate the limit of x approaches a of f of x, which is given the variable L. It states that for every number epsilon greater than 0, there will be a corresponding number delta greater than 0, such that the absolute value of f of x minus L is less than epsilon, whenever the absolute value of x minus a is less than delta but greater than 0. You might be wondering what it actually means. So let's look at a graphical interpretation of it. As you can see, as the graph is approaching the y value of L, which is our limit, we have placed an epsilon both above and below it. This is our bound, and as you can see, it corresponds to a certain delta on the x-axis. With different values of epsilon, there will always be a delta, so we know that this holds true for the limit. We have looked at how to define limits. We now can look at how to solve them. For example, let us take this case. In this case, we are trying to find the limit of the function as it approaches the x value, which is shown with a horizontal line. As you can see, it just approaches a certain point on the function. To find the limit, we would just plug in the x value into the function. A different case. In this case, the function is almost exactly the same as in the last time. However, at the point that we are taking the limit, the value is different. So the function is no longer continuous. If we take the limit of this function, we will have the same value as in the last function, because as the function approaches the value, we will still have the same trend. So it will be still approaching the same y value. However, the value of the function is different. Let's look at this final case. In this final case, we will be taking the limit as the function approaches 0. However, as you look at the function, the value approaches infinity if you approach from the right side, but it approaches negative infinity if you approach from the left. In this case, the limit is undefined because it's different as you approach from both sides. There is a way of writing these limits as a single-sided limit. To write a single-sided limit, you would write a limit as you normally would, except for you would put a superscript of a plus or a minus to indicate from which side you're approaching. The plus superscript signifies that you're approaching from the right side, while the minus superscript means you're approaching from the left. In this case, if you have the limit as the function approaches 0 from the positive side, you would get infinity, or as it approaches infinity, it's actually undefined. However, as you approach from the negative side, you will get also undefined, but it will be approaching negative infinity.
Now that we explored the mechanics of limits, let's apply them to some real problems. Here is our first problem. It's a fairly simple problem because there's no discontinuity at x approaches 3. Because of this, we can plug in 3 into the equation. So you get 3 squared plus 3 times 3 plus 2, which is equal to 20. As you can see, our second problem is more complex than the first. This is because if you plug 2 into the equation, you get a denominator of 0, which does not work. Therefore, we just start by factoring. The numerator factors into quantity of x minus 2 times the quantity of x minus 5, and the denominator factors to a quantity of x minus 2 times the quantity of x plus 2. Now the two x minus 2's in both the numerator and denominator cancel out. Now we can plug 2 into the equation. When we do that, we get 2 minus 5 divided by 2 over 2, which is equal to negative 3 over 4. This problem is similar to the last one because we cannot just plug the number into the equation because we'll get a denominator of 0. Therefore, we have to find a way to work around. First, we place the two fractions in the parentheses under a common denominator. Once we reduce this, we can multiply two fractions together. We see that the x's on the top and the bottom cancel out. Now we can place 0 into the equation, and this gives us negative 6 over 25 minus 0 squared, which is equal to negative 6 over 25. Now it is time to work with limits and with infinity. We start by dividing both the numerator and denominator by the largest power of x in the denominator. In this case, it is x squared. After we do this, we get x plus 1 over x minus 100 divided by x squared, all divided by 2 minus 5 over x. We learned previously that any integer divided by x, where x approaches infinity, approaches 0. Therefore, we end up with 7 over 2, which is our answer. Now it is time for an exercise in continuity. Remember, in order for a function to be continuous at a point, the function has to exist at that point, the limit has to exist at that point, and the limit has to equal the function. In order to find if the limit exists at that point, both sides have to be equal. To find out the limit from the left side, we plug 3 into x cubed minus 1, and we get 26. To find it from the right side, we plug 3 into x squared plus 14, and we get 23. Since those two numbers are clearly not equal, the limit does not exist at that point, which means the function is not continuous at that point.
Well, that about wraps it up for BC Limits. Thank you for watching, and we hope we've been helpful to your BC work. Good luck.